In this video, we'll be going over our findings for Ninja.io, a physics-based 2D shooter made by a single man. We'll cover how we were able to manipulate the in-game economy, develop client cheats despite strong server-side validation, how we took the site offline, and stopped just short of taking it over completely. After finishing up with Narrow 1, we wanted to continue game hacking and were hungry for a new target. In this game in particular, our good friend and member of the organization who goes by the name Rat was being picked on by trolls for his sheer inability to play the game. Sorry, Rat. Eventually, well, sooner than you might expect, his patience expired. He'd had enough. There were a lot of things he could have done in response, but if you think he intended to get good, you must have lost your mind. No, the plan was simple. Make money and cause mayhem. The first thing we did was gather enough wealth to buy the trolls' collective houses. Well, if the in-game currency had any real-world value. We did this via a series of API vulnerabilities. The game API had several ways of rewarding players for coming back and playing over longer sessions, all of which required watching ads to claim the reward. Using a direct call to the API endpoint used to issue rewards after an ad roll, we were able to bypass the requirement to load or watch the ad entirely. Of course, that's pretty basic, and while it does impact the game financially, likely not much more than the ad blockers that many users run already. If you've seen our last video dissecting Narrow 1, you'll understand the prevalence of race conditions in video game economies. If you haven't yet, you can watch that for more detail. To keep it brief, a race condition exploit takes advantage of concurrent processes to disrupt the intended order of operations. This causes actions to occur at unintended times, and in the case of an exploit, in a way that benefits the attacker. By sending multiple requests to a rewards endpoint, all in a single packet, Witchdoctor was able to multiply the reward by 3 to 5 times. Now that we know race conditions are possible in one context, we can safely assume that there may be other contexts that use the same vulnerable implementation. The obvious attack surface to use here is the item shop, but when we systematically try this exploit everywhere the site uses gold, we find even more vulnerabilities. For example, we can multiply gold in the same way with a single packet attack when sending it to other players. This does, however, leave the sender account with a negative balance, in which case the account can simply be disposed of, and encased in concrete and thrown in the... Sorry, I'm getting ahead of myself. We can spend more gold than we own in several places, of course, including the item shop. You may recognize this as the vulnerability we called loan sharking in our last video. Despite these findings and their capacity to be chained together for multiplicative gains, acquiring a large amount of gold still required multiple accounts. So necessarily, our first step was registering our disposable accounts. And there were two methods of account registry based on whether the user signed up with an email or not. When registering with an email, users are rate limited using the email address as the primary identifier. When registering without an email, IP address is used as the identifier, and the user will be rate limited to a handful of accounts per day. Additionally, only reputable mail clients such as Gmail or Outlook could be used. Obviously, it wouldn't be practical to register a new email address for every game account, and even less so to find a new proxy every time we got IP rate limited. But we didn't have to. Rat realized that since Gmail ignores extra dots when resolving email addresses, we can reuse the same email address with periods at different positions. By registering a Gmail address of the maximum length, 30 characters, and signing up for the game with every possible dot variation, we would be able to create over 500 million accounts from a single email address. We can also amplify this and create even more accounts by once again employing a race condition identified by Witchdoctor. In simple terms, X accounts are created before the email can be marked as taken. In our testing, we achieved 6 to 7 times amplification here, so the theoretical max, ignoring server limitations, is approximately 3.5 billion accounts from a single email. Alright, so we have more alts than we know what to do with, but the developer is anything but stupid here. He knows that by requiring accounts to have several hours of playtime, he can raise the bar for effort when creating a gold farming bot significantly. Specifically, accounts needed to have played the game for at least 2 hours, and of course, we're not afraid of a challenge, so we needed our bots to farm playtime as well. We didn't want to get bogged down with reversing the JavaScript yet. It was a lot to make sense of, and in this instance was not the simpler option, so Rat got started with protocol analysis. The keep alive mechanism worked by having the server issue a ping frame requiring a response from the client approximately every 8 seconds. Despite successfully implementing this, we next found ourselves being kicked for idling. Fortunately, the packets sent when firing a weapon were not hard to pick out, so we were able to make our bots shoot occasionally and avoid being kicked much more reliably. Of course, they were still pretty obvious, and we were concerned that the dev might get spooked and start trying to stop us before we even had time to finalize our testing and submit a report. To address this, Rat captured some frames from real gameplay and saved the sequences as actions in the bot script. After performing one action, the bot will randomly pick another. Immediately, we were being called out much less frequently. We next automated claiming rewards on several of our alt accounts until they had accumulated over 1,000 gold each, which was the maximum amount players could transfer at once. We then used the transfer race condition to send 3,000 to 4,000 per alt to the central account. Witchdoctor decided the best use of our newfound wealth was to purchase several expensive hats. As a result, we now owed the game almost 18,000 gold. It was time to move on. Next, we began poking around the game object in the client-side JavaScript. This time, as the name was predictable, it was identified by Witchdoctor using the console and a little guesswork. We came to the conclusion that unlike in Narrow 1, attributes like position, flight duration, and ammo count are all properly validated server-side. Does this mean we're not able to cheat? Of course not. We weren't able to lie to the server, so instead we had to focus on what it tells us, where it might be oversharing. The positions of each player were sent by the server and then stored and rendered by our client. The issue with these kinds of implementations is that the client knows more information than it displays to the user. If we poke the client in the right way, we can expose this hidden information. This is the basis for wall hacks and similar client cheats. By simply moving the camera or canvas in JavaScript beyond where the client would normally place it, we can peek at players who should be out of sight. The first approach we applied this concept to was a freecam cheat. By nulling the camera's target attribute, we can cause it to follow the cursor indefinitely. The next iteration was a zoom cheat, which we achieved by setting the target scale of the canvas. Finally, the last client cheat we implemented was an aimbot. Witchdoctor first sorted all players not on our team by approximate distance. Our method for doing so was simply adding the distance on both axes. We then selected the closest opponent and Rat wrote a script to simulate moving the cursor to the enemy's predicted position. Using their current position and their velocity, we can directly calculate where the player will be. After we have a lock on the enemy, we trigger an auto fire and the whole process beginning with the distance sorting starts over. This process is repeated until the aimbot is toggled off. Our suggested mitigation for all of these problems was to implement server-side occlusion. For each client, the field of view would be calculated and the position of players would not be sent unless they were within the field of view. In this case, only audio modulation values would be sent so they could still be heard. The more knowledgeable of you may be thinking, that wouldn't stop aimbotting, it would just limit the range of the aimbot, and you would be correct. If you're wondering why we don't have a suggestion to completely remove aimbotting, the reason is simple. It's just not possible. Even if the game's own code could not be modified directly, the position of the players could be determined from packets received and packets sent could be modified accordingly. This was the method used in the 1990s to create Quake aimbots, which are today argued to be the first of their kind. Take it a step further, even if packet manipulation could be entirely prevented, aimbot would still be possible via a combination of computer vision and mouse automation. The team was just wrapping up when myself, Tonabrix, popped back in after being on holiday. I began poking at the API endpoint for user stats, which took a numeric user ID via the URL path. If you take nothing else from this video, one thing you should is that eval is evil. When a user can input text that is evaluated by a server, they are wielding a dangerous level of control. When testing different invalid inputs to see how the server responds, I found that it would accept things like negative numbers, floating points, even scientific float notation. Pushing this further, I realized that entire mathematical expressions like 2 + 2 would be properly evaluated. The goal now is to identify exactly what software is evaluating and what limits it places on us. In the very beginning of the hunt, we found that the server discloses excessive information about the software it's running. In particular, we knew that the backend ran on the Slim PHP framework. So I threw in a random payload that would only run on PHP by calling a specific function in that language. It returns a 500 server error, but why? This turned out to be a result of the output of eval being turned into an integer. When you try to use a function that doesn't return a number, and then the code attempts to convert its output into a number, it errors out and we get back a 500 server error. So I try a PHP function that will return a number, namely hash functions like MD5 and SHA-1. Those do return a 200, but the response claims that the player ID doesn't exist. Finally, we do some math with the MD5 calls to reach a known user ID with the payload shown on screen. Okay, so we found a PHP eval injection, meaning we can cause our code to be executed server-side. But it's not game over. Not yet. Like the side dishes in a Nikocado mukbang, the restrictions on what we could do were grotesquely abundant. I needed a simple way to demonstrate impact without using any filtered functions or characters. After a bit of googling for PHP operators that might cause load, I decided to make use of PHP's weirdest operator, the spaceship. The spaceship operator compares two values and will return -1, 0, or 1 depending on the inputs. This doesn't matter too much in context. The key for us is that it's a relatively slow operation. By chaining these spaceship operators together, we can exhaust the server's CPU and cause denial of service. We had figured that we'd just send one batch of requests to the API, it would hang for a minute or two, and we'd simply demonstrate impact for the RCE without having to spend time actually bypassing the filters. But a few minutes passed, and then a few hours. Needless to say, we had gotten ourselves into a bit of a pickle. As we watched the Ninja.io community Discord, we saw several of its members understandably confused and frustrated. We immediately contacted the developer. We explained the cause of the disruption, and soon after reported all of the vulnerabilities we had discovered during our hunt. To recap, we had two mass registration exploits, the Gmail.trick and the race condition amplification. These could be combined to achieve more impact, but one was enough to create more accounts than we could ever need. We had numerous economy exploits and could perform loan sharking anywhere we could spend money, including the item shop, account-to-account gold transfer, and a few that we didn't mention, like clan creation. Although the server-side validation was strong, we were able to make freecam and zoom cheats to exploit the fact that there was no server-side occlusion. And obviously, the denial of service from the remote code execution we found. If we had more time to research, it was extremely likely that we would have been able to turn the RCE into full control over the server. But alas, with the disruptions we had caused already, we decided it was best to leave it at that and not risk any more incidents. The developer swiftly responded, thanking us for reporting and noting that he was aware of some of the race conditions in theory, but was convinced that they were impractical. He also clarified some things about the auth system that we had misunderstood, pointed out that the RCE would be #1 priority, and explained that the technical debt that comes with server-side occlusion would make it impractical to implement. Soon after, he had resolved the issues we highlighted and posted an announcement explaining what had happened and what our organization does. He also let us know that he would be happy to post our video in the Ninja.io community Discord when it was ready, so if you're here from that Discord, hope you enjoyed. A big thank you to the developer Buiz for his response. And to everyone else, thanks for watching, stay vigilant, and we'll see you next time.